All right, welcome back, Physics 11, to another exciting episode of Mr. Wellsby Gives You Some Notes. Today we're going to be talking about vector addition. So we kind of had a preview of this during our last video where we were talking about how two vectors can be considered as summing to one. So we've sort of had a sneak preview already. Today we're going to go into a bit more detail. So remember, when we draw vectors, we represent them as arrows. And in this case here, the direction is given by the direction of the arrow. And we also have the magnitude, which is given by the size of the arrow. The size of the arrow is given by gives us the magnitude. The longer arrow represents a larger magnitude, larger force, larger distance, etc. Now, whenever we add vectors, we use something you're going to hear many times, which is we add them tip to tail. So what I mean by that is when we have two vectors. So let's say I tell you, for example, person A took a walk 3 meters to the north. Then they also took a walk 3 meters to the east. So what we're doing in this case, we're trying to find out how far their total displacement is. How far have they moved from where they started to where they finished? And we know these are our two vectors. We've got one vector that's 3 meters to the north, and we have another vector that's 3 meters to the east. So when we draw this out, it's going to end up looking like this. We add our two vectors, and when we draw the first vector, from the tip of that arrow, we attach the tail of our second arrow. So I'm going to take, for example, this arrow here, and I'm going to move the tail of the arrow over to the tip of this arrow here. So I'll draw this way, and this gives us our tip-to-tail addition. So this is how I've added two vectors together, added them tip to tail. And when we want to find out our resultant vector, we simply draw one arrow from start to finish. So we started this, our very first arrow number 1 was this point here. We added this here, so the very, very start. And when we added our last vector, our second vector in this case, ended up over here. So from the very start to the very finish, we draw one line. Now you may want to draw this as a dotted line. That's totally fine if it helps you remember that this is the resultant vector. So this is the overall vector that we get when we add those other two vectors together. You can think of it as if I walk 3 meters north, 3 meters east, overall I've gone some value that we can calculate from Pythagoras. So this is how we draw our overall resultant vector from the very beginning of the first arrow to the very end of the last arrow. So this is a kind of a challenging example I'm going to give you up ahead here. So please don't feel bad if it takes you a couple of tries, or if you want to pause and restart the video a few times, that's no problem at all. Also, just so you know, some of my sheets I use this notation here, m and s minus 1. This is just saying m, s to the minus 1 means it's 1 over s, right? So you can, some of my sheets I'll have it written this way, some of them will have them written like this. So meters per second, or ms minus 1, means the same thing. So in this example here, a student is in a canoe and they're trying to cross a 45-meter wide river that flows due east at 2 meters per second. Now the student can paddle at 3.2 meters per second. Now before we get started, I want to show you something that I think you're going to find helpful, and I'd really like you throughout the start of the year especially to follow this method. So this method I'm going to give you here is called the DISC method. So this stands for drawing, information, solution, and calculation. Now the reason why I go through this method is because it works. That's the bottom line. Now, human beings are very visual creatures. A huge percentage of our brain is designated for our visual cortex. So our visual cortex is around 40% of our brain. That's our most efficient part of our brain for processing information, which is why doing a drawing first is remarkably helpful. It may seem like it's unnecessary, and especially for some simple problems, you may think it's a waste of time. But trust me when I say this, every student that does drawings will be more successful on average than students that don't do drawings. So I strongly recommend that you follow this method, especially to start, and you can start to pare down as the year goes on. So the first thing I'm going to do here is I'm going to do my drawing here. So this river is going to the east at 2 meters per second. So I'm going to put this as V of the river is 2.0 meters per second. It's flowing to the east. Now this person's canoe is pointing due north. So if this is my canoe here, I'm going to be going due north, and I can travel at 3.2 meters per second north. And what we're trying to find out is, in this question here, how long will it take him or her to cross the river? So the river here is 45 meters wide. So they're crossing this 45-meter distance. They're traveling directly north, so directly across the river at 3.2 meters per second, and the river is going at 2.0 meters per second to the east. So please pause the video and see if you can figure this out for yourself. Hey, are you just waiting for me to give you the answer and not pausing the video? I hope not. I hope you paused it already. You still haven't paused it. You're still waiting for me, aren't you? Shameful. Okay. Hopefully you have paused it. Hopefully you have given this a try. But if you're stuck, not to worry. This is a bit of a tricky question. And the reason why it's a bit of a tricky question is because of this fact here. When you are traveling directly north and the river is directly east, you can see that these two vectors are going to be 90 degrees away from each other. Now what you'll find is that when two vectors are 90 degrees from each other, we don't actually need to take into consideration the other vector. So whatever the speed of the river is, if you're traveling directly north and that river is traveling directly to the east, that speed of the river is not going to impact how long it takes you to get across. So I'll give you another example that might make that easier to believe. You may think I'm just making that up, but I promise you I'm not. Let's say that you are at the airport. And you know, at the airport, they have those moving elevators, those moving escalators, where you stand on there and the whole thing moves to the right to help you walk along with your heavy luggage to make your life easier. So let's imagine for a moment that you're standing on one side of the moving elevator, and the moving elevator is moving to the right, moving this direction here. Now let's say you wanted to walk across this. Let's say the distance here is 1 meter, and let's say you're able to walk at 1 meter per second. How long is it going to take you to get across the moving escalator, the movator? Well, if you're traveling at 1 meter per second and it's 1 meter across, you know that it's going to take you 1 second to get across that moving escalator. Now, does the speed of the movator impact how long it's going to take you to walk across? No, not at all, because you're moving at 90 degrees to it. Now, if it's faster, when you've walked, you may end up traveling a path that looks something like this. If it's quite fast, you might have moved 5 meters to the right in the same time that you've moved 1 meter across, but it's not going to change the amount of time it takes you to get across. Of course, if you're moving slowly, your path might look something like this from an outside observer, compared to moving like this if you're moving on a quite fast movie. So it's a little bit of a tricky question. Once you know that fact, though, then it becomes pretty straightforward. You are traveling to the north, so your velocity to the north is going to be 3.2 meters per second. The distance that you're traveling to the north is going to be 45 meters, and you're trying to find out the time. So here I have written down all the information: velocity, distance, and time. So now I'm going to use the solution. So the solution is that I need to find a formula that relates these three things together. So I've got the velocity and the distance and the time. And we do know a formula relates these three things together. We know that velocity equals distance divided by time. And so if I want to rearrange to find the time, I'm just going to multiply both sides by t. So then I have vt equals d. The t would cancel out on the right-hand side. And then I'm going to divide both sides by v. So I'm going to have t equals d over v. This is going to be 45 meters divided by 3.2. And this is going to be approximately 14 seconds. So 14 seconds is how long it would take me to get across the river. So you can see here the last step is a calculation. So the solution is finding a formula that works, and you rearrange and calculate. So what is the total velocity relative to your starting point? So this is when we're actually using the information that we've learned so far in this lesson and the last. Let's take a look at what we're asking here. We're trying to find out the V total. So I'm going to call this V with a little subscript T. You'll notice I use a lot of subscripts in my lessons. This is just a way to remind me which V I'm talking about. If I call everything V, then how am I going to know which one is the V of the river, which one is the V of the canoe, which one is the V total? So in this case here, I've got two velocity vectors that are going to add together to give me my total velocity. So what I'm going to have is I'm going to have the velocity of the canoe, and to that velocity I'm going to add the velocity of the river, and this is going to tell me my overall velocity. So we know the velocity is not going to be 3.2 because the river is going to move me to the right. So I'm going to have an overall total velocity that looks something like this: 3.2 meters up, 2.0 meters across. I'm going to add those vectors together. So remember, when we add vectors together, we're kind of starting, I wouldn't expect you to draw this part. You're drawing the velocity of the canoe, we're going to add the velocity of the river, and we're going to get the total velocity. So this is the part that I would expect you to draw on a quiz, for example. So let's draw this a bit better. We've got the velocity of the canoe. This is 3.2 meters per second. And then we've got the velocity of the river, which is 2.0 meters per second. And we're trying to find out what the total velocity is going to be. So I'll leave this for you to answer. So please pause the video and give this one a shot, and come back when you're done. Okay, hopefully you have finished already after you've paused it. So the first thing we're going to do is a little Pythagorean theorem. So in this case here, we have 3.2 squared plus 2.0 squared equals the total velocity squared. So if we calculate that, we're going to have 3.2 squared is 10.24. We're going to add 2 squared, which is 4. So VT squared equals 14.24. So VT is going to be equal to the square root of that. And so around VT is approximately 3.8 meters per second. But wait, this is a vector. So whenever we're describing a vector, we can't just stop at the magnitude, because then I'd be asking you, if I wanted to know that, I'd be asking you for the speed. But I really want to know the velocity. So what is the extra bit of information I need when I'm giving a vector? Well, I need the magnitude. I also need the direction. So to find this direction here, I know the opposite is 2.0. I know the adjacent is 3.2. And so, pause it if you don't want me to spoil the surprise, but we're going to have to use tan. So tan of theta is going to be 2.0 over 3.2. And so theta is the inverse tan of 2.0 over 3.2. And theta is going to be approximately 32 degrees east of north. So this is my overall answer: 3.8 meters per second at a direction of 32 degrees east of north. That is my total velocity relative to my starting point. So even though I'm going at 3.2 directly north, the river is pushing me down the river and giving me a little bit of extra speed. So I end up going a little bit faster, 3.8, and I also end up going off to the right a little bit by 32 degrees. Now, maybe a trickier question. In this question here, the person in the canoe needs to end up directly north from the starting point. They don't want to go down the river. Let's imagine here, so we've got our river. I'm going to redo my drawing. So here's my river. The river is 45 meters across. But let's say when the canoer is here, they are on the edge of a terrible, deadly waterfall. So if he goes to the right, he's going to be dead. He's got to go directly across. So let's think about what those vectors are going to be. So if the river is moving this direction here at 2.0 meters per second, and I know that I'm going to be having an overall velocity direction of being directly across. So my VT is going to be in this direction here, what direction would my canoe speed have, or what direction would my canoe be having to travel in order to end up going straight across? So what I'd like you to do is try drawing your vector triangle. And if you want a little bit of a hint, you can pause the video after I say this. What I'd like you to do is think about this statement again, the same thing that we did before. So in this case here, we have the velocity of the canoe. We're going to add the velocity of the river, and this is going to give us our total velocity. So if we look at this statement here, think about what our vectors are going to be. We know what our river velocity is, and we know what our total velocity is. So what would I need to add? What direction would I need to draw the canoe velocity in order to end up going straight? You can visualize it in your head. You can try and visualize it with this equation here, but give this question a try and see how you do. And if you don't get it the first try, don't feel bad at all. It's definitely a tricky concept to do this way. So give it a shot. If you don't get it right the first time, please just rewind to here and try it again. Okay, so hopefully you have realized that in order to get across the river going straight across, you are going to need to aim your canoe a little bit to the left. So it's going to look something like this. We have the canoe velocity plus the river's velocity is going to equal this velocity that goes straight across. So if I try and draw this out, this is what it's going to look like, and this is why your numbers may not have worked out the first try. So in this case here, I'm going to add this velocity here. So this is the velocity of the canoe plus the velocity of the river, which is going straight to the right. So this is going to be the velocity of the river. And these two together are going to equal my total velocity. So this is going to be V total. Now, if we're trying to fill in our triangle, what are the sizes? What are the sizes of these sides, or the sizes of these vectors? Well, this is going to be 3.2 meters per second. And you'll notice a big difference here. When we looked at this example here, what side was the hypotenuse on the previous question? So in the previous question here, the hypotenuse was the total velocity. But that's not always going to be the case. And in this case, it's in fact the canoe's velocity that's going to be the hypotenuse. So you're going to be paddling away as hard as you can and getting up a relative speed of 3.2 meters per second. But the river here is at 2 meters per second, and it's actually pushing somewhat against you. You're going to the left, and it's pushing you to the right. So it's going against you in this case here. So is this the total velocity going to be more or less than 3.2? Well, if 3.2 is the hypotenuse, we know this has to be less. So we're still going to use Pythagorean theorem. We have Vt squared plus 2.0 squared is going to equal 3.2 squared. So side A squared plus side B squared equals side C squared. And now we're just going to rearrange. So Vt squared equals 3.2 squared minus 2 squared, so minus 4. This is 10.24, I think, 3.2 squared. Yeah, 10.24 minus 4 gives us 6.24. And so Vt is going to be the square root of 6.24, which is going to be approximately 2.50 actually. So it's pretty close to 2.50 on the dot for the total velocity. So if we're looking at this question here, the question's really asking us what heading should it be. So we didn't need to solve this, but we are going to need it for part D. So we're just going to store this information away. The total velocity is 2.5 meters per second going across the river. If we want to know the heading, though, this is where we're going to need to use a little bit of trigonometry. So we know the opposite, and we also know the hypotenuse. So opposite and hypotenuse, what would that be? Well, it is sine. So sine of theta is going to equal 2 divided by 3.2. And so theta is going to be the inverse sine of 2 over 3.2. And that's going to be 39 degrees. So theta equals 39 degrees. And we're going to have to travel west of north. So this is the actual answer that we need for part C, 39 degrees west of north. And now that we've already got our speed going across the river here, we're just about done. So how long will it take him to cross the river at this heading? Well, here's the information we know. Our distance to the north is still going to be 45 meters. Our velocity to the north is now going to be, what did we say it was? 2.50 or 2.5 meters per second. And we're trying to find out the time. So I've done my drawing in the previous part. This is my information. The solution portion of this is our formula. V equals d over t. Velocity is displacement over time. And so again, rearrange it the same way we did above. T equals d over v equals 45 over 2.5. And that is going to be exactly, or pretty close to 18 seconds. So 18 seconds is how long it would take the canoer to get across the river. That's all we're going to do for these notes. Page 2 we are going to finish in class. It's a bit more complicated, and I'd like to teach it with a bit more support in place. So hopefully you enjoyed this lesson, and as always, email me if you have any questions. Thank you.